Welcome to the deep dive. Today, we're plunging into the fascinating realm of multiplace hyperbaric chambers.
Mm,
Forget those single-person tubes you might have seen. We're talking about these really sophisticated medical environments
right.
and apparently incredible strides in safety and even, patient comfort are making treatments possible that were, well, previously unimaginable.
Exactly. It's more than just pressure. We're
Yeah.
exploring this convergence of like engineering, medicine, and really stringent safety protocols.
And to guide us through this deep dive, we'll be drawing on the authoritative textbook, Hyperbaric Medicine Practice,
Yep. Good source.
and a chapter specifically dedicated to these multiplace marvels. Our mission today is to unpack exactly what these chambers are, how they actually function with all their intricate systems, the critical safety measures that are, well, literally built into their core, and ultimately why they stand as the preferred choice for certain kind of complex medical situations.
It's a highly regulated field, for sure, and fascinating.
Definitely. So let's get started. When we talk about a multi-place hyperbaric chamber, what are the sort of fundamental things we need to understand right off the bat?
Well, I think the first key thing is that these aren't just, off-the-shelf pressurized rooms. In Europe, they're rigorously certified. Class IIB medical devices.
Class IIB, what does that really mean in practice?
Think of it like a really high-quality stamped under Directive 9342 EEC. And these guidelines, MADTV 2.41, it basically ensures they meet incredibly high standards for safety, performance. It impacts everything from materials to how they're made.
Okay.
You'll always see the European community marking on them, and that's backed by a huge technical file manufacturers have to keep.
So super regulated from the ground up in Europe. What about here in the US? Is it similar?
In the States, the main framework comes from the National Fire Protection Association, NFPA, specifically NFPA 99, the 2015 version, Chapter 14.
Okay.
And that chapter defines the requirements for what they call Class A hyperbaric chambers. Crucially, those are the ones designed for 2 or more people at the same time.
Got it. Class A for multiple people. So fundamentally designed for a team approach, maybe for sicker patients.
Often, yeah. Or just treating more people efficiently. So what do they actually look like? What's the structure?
Yeah, what's the physical setup?
Well, the typical image is a cylinder, right? That shape is just optimal for handling the pressure.
Makes sense.
But there are exceptions. Sometimes they're square, like the one at Karolinska Hospital in Stockholm. Probably for, better internal space or accessibility.
Interesting.
But generally, you've got 2 main parts connected. The big one is the main treatment chamber where patients get the therapy. And then there's a smaller attached compartment called an airlock.
The airlock, that sounds critical, like on a submarine or something.
Exactly like that. It's
Right.
absolutely vital. It's the transition zone.
Yeah.
It lets staff get in and out of the main chamber without messing up the pressure inside.
So you don't have to decompress the whole main room every time someone needs to enter or leave.
Precisely. The airlock can be pressurized or decompressed independently. So someone steps in from outside, they close the outer door. The airlock pressure is raised slowly to match the main chamber.
Okay.
And only then can the inner door be opened safely. Same process, just reversed for getting out. Our sources even have diagrams showing exactly how that works.
That's a clever system. Keeps everything stable. What about the doors themselves? They must need to be incredibly strong and airtight.
Oh yeah, engineered for safety, reliability. They're airtight, usually using big O-ring seals to keep that pressure integrity.
Right.
But interestingly, for safety, they generally don't have locking mechanisms you can use while it's pressurized.
Really? Why not?
So nobody can get accidentally trapped inside. They're designed to just open passively, kind of push open once the pressure on both sides is equal.
A built-in safety feature.
Exactly. And many chambers also have a rectangular door option, which makes a huge difference for getting patients in on stretchers or wheelchairs.
Good point. Accessibility. And what are these things actually made of, the main structure?
The structure itself is usually carbon steel, chosen for strength, obviously, for pressure vessels. Then it's coated with something durable like enamel epoxy paint, stops corrosion. But inside, the finish is really important. It's typically an inorganic zinc epoxy that's fire retardant.
Fire retardant. Okay, another safety layer.
Absolutely critical. You don't want toxic fumes or anything combustible building up if, God forbid, there was a fire inside that pressurized environment.
Makes total sense. It seems like safety is just built into every single component. Our sources also mention something called an object pass-through lock. What's that about?
Ah, yeah, that's a neat feature. Really practical. Imagine like a small 2-door box built into the chamber wall.
Okay.
It's interlocked, so only one door can be open at a time. It lets staff pass small things, maybe meds, documents, certain small devices in or out while the main chamber stays pressurized.
Oh, like a little mini airlock just for stuff.
Yeah, pretty much. You just quickly pressurize or decompress that little box to match whichever side you're opening the door to. Avoids a whole cycle just for, say, a syringe.
Very efficient. Keeps the treatment going. What about seeing inside? Are there windows or portholes?
Yep, definitely.
Yeah.
Strategically placed transparent portholes in the walls. These aren't just simple windows, though.
Right. They'd have to withstand the pressure.
Exactly. They're usually made with an outer layer of perspex, that's a tough acrylic, and then a thick inner layer of acrylic safety glass. All has to meet strict ASME PVHO regulations. That's for pressure vessels for human occupancy.
Wow, okay.
Often they're double layered for extra safety, and there's even a tiny equalization hole in the inner layer to manage any pressure difference between the layers.
Huh. Clever.
And then you've also got smaller viewing ports, sometimes called observatories, usually on top. They do double duty.
Which is?
Housing the internal lights needs to be bright, at least 300 lux, but dimmable way down to maybe 10 lux. And also holding video cameras.
Ah, for monitoring.
Continuous internal observation, yeah. And recording, too. You need to see what's happening inside at all times.
So constant monitoring is key. What if the main power goes out? Is there backup lighting?
Oh, absolutely. Given how critical it is, there's always an independent emergency lighting system. Kicks in automatically if the main power fails.
Sure.
Ensures you can still see inside. That backup system follows European standard EN 14931.
Okay.
It's also interesting. During construction, they plan for more pipe penetrations and cable connections than they need right away for future instruments or controls.
Smart planning.
Yeah, and any unused ones are just sealed up, completely airtight, obviously. Got to maintain that pressure integrity.
Okay, so the construction is clearly, incredibly complex. Huge emphasis on safety, redundancy. Let's shift to how they actually get pressurized. How does that work?
Right. This is another really key safety difference, especially compared to single-person or monoplace chambers.
How so?
Multiplace chambers are pressurized using compressed air. Just regular air, basically, but compressed, not pure oxygen.
Ah. Okay, that seems like a huge safety advantage right there. Reduces the fire risk inside the main chamber itself.
Massively. That's exactly why. The atmosphere inside is essentially just highly compressed air.
So how do patients get the oxygen they need for the therapy then?
They get their oxygen, or sometimes other gas mixtures, through separate delivery systems. Things like masks or specialized helmets, or even endotracheal tubes if they're on a ventilator.
Okay.
These are all hooked up to a completely independent gas circuit. And importantly, any gas the patient breathes out is actively vented outside the chamber, not into the room air.
Got it. So the oxygen is contained. What about the systems actually compressing and delivering all that air? Are they heavy duty, redundant?
Oh, yeah, absolutely.
Wow.
The systems for the main chamber and the airlock are separate and built with multiple safety layers like you'd expect. Dual power supply for the air compressors, usually, with automatic and manual bypasses in case something fails. Got to keep that pressure stable. And the system needs to pump a lot of air, maybe 30 to 40 cubic meters per minute, to pressurize things reasonably quickly. Plus, they put silencers on the airlines.
Why silencers?
To cut down the noise inside the chamber. Makes it much more comfortable for the patients during the treatment.
Good point. So it's a controlled, relatively quiet process. You mentioned masks and helmets for the oxygen delivery. How do those work specifically?
Yeah, there are mainly two types. One uses what are called demand valves. They work a lot like scuba regulators, actually.
Okay.
You connect them to a snug-fitting Aronis wool mask, covers nose, and mouth gets a good seal. So the patient breathes pretty much pure oxygen on demand,
Right.
and not the chamber air. Exhaled gas goes out through a separate corrugated tube.
Right. And the other type, helmets.
Yes, helmets. These use dispensing controllers that provide a continuous flow of the gas mixture, keeps the helmet inflated, and delivers the therapy.
Sounds maybe more comfortable than a mask?
Can be for some, yeah. But there's a critical safety point with helmets. If they leak, and they sometimes can, that leakage puts extra oxygen into the chamber environment, increasing the overall O2 concentration, which of course significantly bumps up the fire risk.
Oh, I see the problem.
Exactly. So because of that potential hazard, European rules often limit how many helmets you can use at the same time inside one chamber.
Wow. Fire safety again. It's clearly just woven into every single decision. What other fire measures are in place? Prevention or response?
You're right, it's absolutely central. The whole fuel system, the medical air distribution, it's all meticulously controlled from a central console. Lots of valves, solenoid ones, manual bypasses for emergencies.
Okay.
And there are sensors inside the chamber constantly monitoring the oxygen level. If it creeps up past a set limit, usually around 23.5%, the system can automatically switch patients off their oxygen masks and onto just breathing regular medical air through masks to quickly dilute the atmosphere.
That's smart. An automatic safety override.
Yep. And there are also specific valves designed to physically prevent someone from accidentally just flushing pure O2 straight into the chamber. And then you have the water sprinkler system.
A sprinkler system inside a sealed, pressurized room. That's hard to picture.
It is a striking image, isn't it? But it's a critical safety component. It can be in the main chamber or the airlock or both, depending on the design.
And it's not just like a regular office sprinkler, I assume.
Not at all. It's a high-pressure deluge system. Uses compressed water, designed to dump a huge volume of water extremely fast. Needs to maintain pressure over 8.5 bar, deliver at least 50 liters per square meter per minute.
That sounds like a lot of water.
It is. It could be around 1,000 liters per minute total for a typical chamber. Massive amount delivered almost instantly.
How is it triggered?
Usually there are dual opposing fire extinguishing systems.
Yeah.
CE identified, so they meet those EU standards. Activation needs 2 separate sensors to detect flames simultaneously within like 1 second. Helps prevent false alarms.
Okay, very fast, very specific trigger.
Right. But there's also a manual override. You can deactivate it within maybe 3 seconds if something non-fire related triggers the sensors.
Good.
Plus, the operator can manually trigger 2 different water spray systems from the console, or even from inside the chamber room. And there's a manual fire hose, too.
So multiple layers of activation and intervention?
Absolutely. And if the automatic sprinklers do go off, the system is designed to immediately cut off all oxygen and breathing gas flow to the patients.
Wow.
And simultaneously trigger a rapid decompression through a bottom valve in that section of the chamber.
So it fights the fire and starts venting the chamber at the same time.
Exactly. The water itself comes from high-pressure cylinders, like diving tanks, 200, 220 bar, with pressure reducers to deliver it at the right sprinkler pressure. It's a really robust, multi-layered fire suppression strategy.
Truly sounds like they've thought through every angle on fire safety. Given all that, what kind of things are absolutely banned from going inside?
Yeah, the list is pretty strict because of that compressed air environment and the potential for oxygen enrichment near breathing devices. So absolutely forbidden. Anything creating a spark or flame. Lighters, matches, those little gas hand warmers.
Makes sense.
Battery-powered electronics are generally a no-go too. Phones, remotes, music players. Risk of battery failure, sparks.
Okay.
Clothing made entirely of synthetics isn't allowed either because of static electricity risk.
Right, static sparks.
Any medical gear or even furniture that hasn't been specifically certified for hyperbaric use is out. Too much unknown risk. Patients also need to remove cosmetics before putting on oxygen masks. Some ingredients can be problematic.
Cosmetics, huh?
Yeah, and surprisingly maybe, newspapers are often banned too. Something about the oily ink being potentially flammable under pressure.
Newspapers. Okay, that's one I wouldn't have guessed. So what can patients bring in? It must get boring during those long sessions.
They can usually bring things like magazines, paperback books. Eye shades are fine if they want to rest. Pencils for writing. Ballpoint pens are often okay, though there's a small risk of ink leakage from the pressure change.
Right.
If someone has an implanted medical device like a pacemaker that's specifically approved as hyperbaric eligible, that's okay. But definitely a warning against any implanted device that hasn't been tested and cleared.
Big caution there.
Yeah. And soft contact lenses are usually permitted too.
Okay. That gives us a clearer picture. Now, who's actually in the chamber with the patients during treatment?
Right. During a typical session, maybe 95 to 115 minutes at 2.0 to 2.8 times atmospheric pressure, sometimes longer for decompression sickness. There's always a trained hyperbaric chamber attendant inside. Could be a tech, a nurse, or doctor, depending on how sick the patients are and the facility's rules.
And these attendants are under pressure too, breathing the compressed air. That must have its own risks, right? Like the bends for divers.
It absolutely does.
Yeah.
Decompression sickness is a real concern for the attendants too, so they follow very strict safety procedures.
Like what?
Mainly sticking to the U.S. Navy's no decompression limits. These tables tell you how long you can safely stay at a certain pressure or depth.
Okay.
And if they're inside beyond a certain time limit, the attendant will actually switch from breathing the chamber air to breathing pure oxygen through a mask for a period.
Ah, just like a diver doing deco stops.
Sort of, yeah. It helps reduce the nitrogen loading in their tissues and speeds up the nitrogen washout during the slow decompression at the end. Helps prevent the bends. Figure 7 in our source shows these protocols.
So it's like controlled diving profiles, but inside a chamber. Fascinating. What about medical devices needed inside for patient care? Must be tricky.
Extremely tricky and absolutely critical. Any electrical medical equipment used inside, especially for ICU-level patients, must be specifically certified for hyperbaric oxygen environments.
Why the special certification? Pressure effects? Fire?
Both. The increased pressure can mess with how some devices work. And the fire risk, even though it's mitigated by using compressed air, is always higher with any potential ignition source in an oxygen-available environment.
Makes sense.
If, in a rare case, certified gear isn't available for something essential, the chamber physician takes direct personal responsibility for using that uncertified device safely.
High stakes. So it's not just wheeling in standard hospital equipment. What are the key things they look for in hyperbaric certified devices?
Several vital points. First, the device has to maintain its settings accurately despite the pressure changes. It can't drift.
Right.
Second, it has to stay fully functional, adjustable throughout the whole treatment. Third, if it's battery-powered, it needs serious autonomy, like enough power for at least 1.5 times the planned treatment length, just in case.
And a buffer.
Yeah. Alert thresholds on monitors might need adjusting too because of how oxygen behaves in the blood under pressure. And a basic principle is always minimize personnel and equipment inside whenever possible.
Keep it simple.
It's exactly. Continuous vitals monitoring is obviously key. ECG, heart rate, blood pressure, both invasive and non-invasive. Interestingly, for blood pressure cuffs, they prefer to inflate them using the chamber's compressed air.
Why is that?
Safer, apparently. And it doesn't drain the batteries on portable pumps.
Okay.
Pulse oximetry, SpO2, is also used routinely. But, and this is really important, SpO2 measures how saturated hemoglobin is. It doesn't really show the big increase in oxygen that's just dissolved directly in the blood plasma under hyperbaric conditions.
So the SpO2 reading might look normal or high normal, but the patient is actually getting way more oxygen delivered to tissues.
Precisely. It's a limitation you have to understand in this environment.
That's a crucial point. Now, the sources specifically called out continuous infusion pumps and hyperbaric ventilators. Why are they so important, especially for ICU patients in the chamber?
Well, infusion pumps are essential, right, for giving continuous IV meds to critically ill patients. The pumps used inside have to allow adjustments during the session, and again, that battery life needs to be rock solid, 1.5x the treatment time at least.
Got it. And the ventilators.
Equally critical if a patient needs breathing support. These aren't standard ventilators. They have to deliver steady gas flow, keep a constant breathing rate despite the big pressure swings.
Right, the changing density of the air must affect things.
Exactly. They also need various ventilation modes, VCV, SIMV, PCV, pressure support, plus PEEP settings. And you guessed it, enough battery power.
You mentioned the increased air density. How does that affect breathing, and how do the ventilators cope?
Yeah, higher pressure means denser gas. That increased density makes it physically harder to move air in and out of the lungs. Can lead to hypoventilation, not breathing out enough CO2, just more work for the patient to breathe.
So the ventilator has to overcome that.
Right. There are basically two types. Constant volume ventilators try to deliver a set volume of air with each breath. But as density goes up, the flow rate might drop, reducing the actual volume delivered. So these often need manual tweaking as the pressure changes.
Okay.
Then there are pressure-controlled ventilators. They aim to maintain a constant pressure during inhalation. The flow might still be affected initially by density, but many modern ones have smart algorithms. They detect flow changes and adjust the pressure automatically to keep the tidal volume stable.
Much more sophisticated.
Definitely. Better for adapting to the changing conditions inside the chamber.
This has been incredibly detailed. It's just abundantly clear now that these multiplace chambers are way more than pressurized rooms. They're, seriously sophisticated, meticulously engineered medical devices.
Absolutely. They represent a huge investment, technically, in safety systems. But they offer unique advantages, treating multiple people, even really sick ICU patients, all at once. That's something you just can't do otherwise.
And that relentless focus on safety just shines through, doesn't it? From using compressed air to the crazy fire suppression systems, the rules about what you can even bring inside.
Exactly. Every detail is considered. The tech advancements have really opened doors for complex treatments in this environment, things that would have seemed impossible before.
Right.
But it absolutely requires that highly specialized gear and really well-trained teams to run everything safely and effectively.
So thinking about all this complexity, the cost involved, It kind of makes you wonder, what's next? What innovations might make hyperbaric medicine more accessible or maybe broaden its use even further?
That's a great question.
And maybe, could lessons learned from other extreme environments, deep sea, maybe even space travel, inspire completely new designs or therapies in this field? Lots to think about.
Definitely fascinating possibilities down the road.
Well, thanks so much for taking this deep dive with us today. Really eye-opening.
My pleasure. Always interesting to explore.